this test, it's a comparison test. It allows us to figure out whether some series converge and whether some series diverge. So unlike the nth term test, we can use this for convergence or divergence. And basically what we're going to do is we're going to compare a series to another series that we know, and we're going to use what we know about that series to determine whether the series converges or diverges. So the first part of it says this. We have a series of terms that are not negative, so they're either positive or zero, and that's important, and we'll get into how we handle that later. But these are all positive numbers, and we want to know whether this converges or diverges. So we're trying to decide whether the series of a sub n converges or diverges. We have this other series that we know that we're going to compare it to. We know that this series converges. So again, we don't know if a sub n converges or diverges yet. We know that the series of c sub n does converge. If the series c sub n converges, then if all of the terms in a sub n are less than or equal to the terms in c sub n, guess what's going to happen? It's also going to converge. So if the terms in a sub n are smaller than the terms in c sub n, and we know that c sub n converges, then a sub n also has to converge. Now there's a little extra piece here that says for all n greater than big N for some integer n. And what that's saying is this comparison doesn't necessarily have to start at the first term. It just, once we get to a certain point in both series, once we get to a certain point, then all the terms after that have to satisfy this. So if we consider these two series here, what series is this? 1 plus 1/2 plus 1/4 plus 1/8 and so on. That's not the harmonic series. That's a geometric series, right? With a common ratio of 1/2. So let's just say, even though this is a geometric series, let's say we don't know that this is a geometric series. We know this geometric series here is going to converge to what? Yeah, it's going to converge to 2. And actually, the value that it converges to doesn't matter, but this one on top converges. Again, let's say that we don't know this is a geometric series for now, and so we want to know whether this one on the bottom converges or diverges. So if I compare each term in each series, what's happening here? Which terms are bigger? The bottom ones, right? So the terms in this one are bigger. So if we have terms in it that are bigger than a term that we know converges, does this help us here? No, it doesn't. Because the terms in the series that we want to know have to be smaller than the convergent series. So does that mean I can't use this? If we continue listing out terms, we're going to have 1 over 16 plus 1 over 32 plus 1 over 64. And here we're going to have 1 over 9 plus 1 over 27 plus 1 over 81. And those are both going to continue, right? Well, we've reached a point here that after this term right here, every term after it in this series is smaller than the terms in this series. You guys see that? So 1 over 81 is smaller than 1 over 64, right? And the next term here would be 1 over 128. The next term here would be 1 over 243. 1 over 243 is smaller than 1 over 128. So every term after this point, the terms in the second series are going to be smaller than the terms in the first series. So it doesn't matter about this, because this is just a finite number here. I don't know what it is. I'd have to get a common denominator to add them together. But this right here is a finite number. And then after that point, if we add these together, we know these converge because they're smaller than these, and these converge. So what does that mean about this series right here, the bottom one? It has to converge. So since every term after a certain point in this term, or in this series, is smaller than every one in the series that we know converges, then we know that the series is going to converge. This comparison test works the other way too, except if our second series is divergent, so if the second series diverges, then if every term in the unknown series is bigger than or equal to the divergent series, then the unknown series is going to do what? It's going to diverge. So if we have a divergent series and then another series where the terms are even bigger, we know that it's going to diverge also. So we can use the direct comparison test to show that a series that's smaller than a convergent series also converges, or a series that's bigger than a divergent series also diverges. This series right here, we saw this earlier. This is the harmonic series. This series we know diverges. And this series right here, term by term, is bigger. So what does that mean about this one? It also has to diverge. So since we have a term that we know diverges, and another series that we know is bigger, term by term, then we know that series also has to diverge.